Here's the example I wanted to look at. Y prime equals x times that bracket 2y plus y to the minus 4. But I see this when I first look at it as first order, because there's only a y prime, equals something of x times something of all y. My first thought here would be separable. But I want to show that it's also Bernoulli. So if I multiply this x through the bracket, and then that gives me 2xy, and bring that 2xy over to the other side, now it starts to look more like Bernoulli. Y prime plus py equals q. It's almost linear, except for it would be linear if that y to the minus 4 wasn't there. So read that as y to the n. That's a Bernoulli equation. So I'm going to multiply the whole thing through by y to the 4 to get rid of that y to the minus 4 on this side. So now it's just x. There's a y to the 4 here. Y to the 4 times y is y to the 5. Common bases add the exponents. And now we're on our way to solving it with Bernoulli. We can see that I want to set v equal to, Bernoulli's a substitution. We let v equal to y to the 5. I'm trying to make this first order linear, but in terms of v, not y. So I let this do the substitution, let v equal y to the 5. You differentiate your substitution, v prime is equal to, okay, the 5 comes down, subtract 1 from the exponent. Chain rule, or implicit differentiation, however you want to think about it, makes it times y prime. So this y to the 4 times y prime I have right here. If I had that highlighted piece times 5, I could replace it with v prime. So I take this equation and I multiply everything through by 5. So there's a 5 here, minus 2 times the 5, that's the minus 10, there's a 5 there. Now I can swap this out for v prime. So v prime minus 10x v, because that was my substitution, is equal to 5x. At this stage, as promised, a Bernoulli equation produces a first order linear, but it's in terms of v. So I can solve this first order linear. I can get the integrating factor, e to the integrate p, so e to the integrate minus 10x. So I do that. I multiply all three sides through by the integrating factor, and now I'm going to integrate both sides. Oh, when I multiply through all by the integrating factor, the left-hand side always integrates to be integrating factor times, I'm going to say y, but I mean v, because that's our dependent variable. And this side integrates however it integrates. In this case, you could use substitution, or I just did it by inspection, and then tack on a plus c when I integrate. So here, we're done with our integrating. There's no more primes. All it's left to do is, everywhere there's a v, put in a y to the 5. So here's our implicit solution. I'm going to get another version of the implicit solution. So this is solved. If I had an initial condition, I could figure out what that c was. So this is the solution. I'm just going to multiply everything through by e to the positive 5x squared, so I could make it y to the 5th equals minus a half plus that constant e to the 5. So here's my another version of the implicit solution. Okay, so I solved the original differential equation by recognizing that I can make it into a Bernoulli equation. And the integration wasn't too bad, right? I had to just integrate minus 10x, that was an add one of the exponent divided by what's up top. I had to integrate this x e to the x squared. I could have done that by a u substitution, or we could just do that as a by inspection one. Now let's look at that same equation, that same differential equation, but this time I'm going with my first instincts. I see it as a separable equation. So I'm going to replace this y prime with dy dx, and multiply the dx side up, divide this bracket out, leave the dy there. It is separable. I can see that it's separable. Integrating the x side, that's going to be straightforward. Integrating the y side, that's not that easy. It's not as easy as the integration we just did in the Bernoulli. The way I'm going to approach it is, I'm going to multiply top and bottom by y to the 4th, so that I don't have any negative exponents, and that gives me y to the fourth so I'm going to multiply top and bottom by y to the fourth. When I do that, distributing this y to the fourth on the bottom across, that's going to make that a 1, and 2y times y to the fourth, 2y to the fifth. So here's the integration with no negative exponents. This one I can do by u substitution. So I'm going to let u equal to the bottom, because I see that a multiple of the derivative is on top. So I'm letting u equal to 2y to the fifth plus 1. You always differentiate your substitution. du dy is equal to, well, in this case, 10y to the fourth. Solve for dy, and now I'm going to replace dy with this du divided by 10y to the fourth, and I'm going to replace this 2y to the fifth plus 1 by the u. So here's my new integration. That 10th, 10 on the bottom, I just brought that to the outside. Now I can integrate this 1 over u. It's ln absolute value of u. All right, now that and I integrated the x side as well. That was just a straight add 1 to the exponent, divide by what's up top, and I get a constant. This time I used k because it's a different constant from when we did the Bernoulli. Let's replace what u is. This is just like in that Bernoulli, right? After we did our integration, we put back what v is. Now I'm putting back what u is. U is 2y to the fifth plus 1. So here's my implicit solution to the same differential equation. Now that doesn't look like this. I know, mumble something about existence and uniqueness, that it must be the same, but let's do a little algebra to prove to myself that it is the same. We're done as far as solving. This is an implicit solution, but let's see if we can make them at least look the same. So I'm going to multiply through by 10 here, just to get rid of this 10th on the side. So the over 2 becomes a 5, and now that's 10k. I understand 10k that's another constant, but let me just keep that as 10k so I can see what happens. I've got ln of something equals, so I'm going to raise each to the e, and that'll e to ln something. That gives me that 2y to the fifth, or 2y to the 5 plus 1. Now it's e to this whole side. I'm going to split that off to be e to the 10k and e to the 5x squared. And I did lose my absolute value bars here. I'm going to account for that later. Let's put them in just so that because I'm not sure if that thing inside the ln was positive or negative. And I'll never know because I don't have any initial condition. So if I get rid of these absolute value bars, then I'm going to have to put, I don't know if the inside is plus or the inside is minus, so I'm going to have to put plus minus here when I get rid of those absolute value bars. So let's just have the plus minus here. That puts the plus minus here. And e to the 10k is a constant, so we've got the plus minus here. I move the 1 over. If I divide everything by 2, I'm going to get minus, so I'm going to divide everything by 2. I'm going to get minus 1 over 2. This constant divided by 2. So this constant is in the same spot as this c. So c, that's my c from the solving it the Bernoulli way. Okay, what's my point with this example? My point is, I had a differential equation and I could have solved it two ways, separable or Bernoulli. My instinct would have been to start with separable, and it wasn't too bad, but maybe Bernoulli was a little bit easier. The integration was a little bit easier. I didn't have to worry about this, absolute value plus minus thing. So I think Bernoulli is easier, but if you just gave me that differential equation, the separable stuff is what I would have done. But you can do either way.